Hello, good morning, friends. I welcome you all for the fourth session of the first chapter, that is combinational logic circuits. So, in the previous session, we have seen still till the implementation of logic gates using mux. Next, the leftover concept in the mux is the applications of multiplexers. The multiplexers, they are used as data selectors. So so while discussing or while introducing the multiplexer itself, we have referred it as a data selector. Means, so as the multiplexer will have 2 to the power of n number of inputs, out of 2 to the power of n inputs, only one input will be selected at a time. To select which particular data input, uh, the multiplexers, they act like a data selectors. Next, they are used to implement the combinational logic circuits. This one we will see in the later sessions. At the same time, the multiplexers can be used to implement the functionality of logic gates also, and these are used in time multiplexing systems, frequency multiplexing systems, as well as these are going to find their important applications in A to D converters, as well as D to A converters, that is analog to digital converters, as well as digital to analog converters. And these are used in data routing as well as waveform generators, and these are going to find their applications in the telephone networks as well as in the communication systems. So in your examination, this question may be asked for the 5 marks, and you are supposed to write at least 5 valid applications for the multiplexers. Next next set of combination logic circuits are demultiplexers. The demultiplexers, they exactly works in the reverse way as the multiplexers do. So here, demultiplexers can be referred as one to many. So as we, while discussing the multiplexers, we told that uh, they they are many to one combination logic systems, and these can be referred as one to many. A demultiplexer is a kind of combination logic circuits uh, that receives the information on single line and transmit the information on one of the 2 to the power of n possible output lines. So for multiplexers, we had 2 to the power of n input lines and only one output line. But here in this logic system, there will be only one input line, and there are 2 to the power of n possible output lines. So out of these 2 to the power of n possible output lines, which particular output line is to be selected, it depends upon the content of the selection lines. So there will be n number of selection lines. As in the case of multiplexers also, there were n number of selection lines. Here also there are n number of selection lines. The contents of the selection lines, they uh, they are used to select one of the data output lines out of 2 to the power of n output lines. So which output line is to be selected, that depends upon the content of the n number of selection lines. So I can refer this system as 1 is to 2 to the power of n, that is there will be one input line and 2 to the power of n output lines and n number of selection lines. Or else you can with the different values of n, I can have the different variants. We will see it in the next slide. Generally, they have one input line and 2 to the power of n output lines and n number of select lines. And like multiplexers, here also there is an additional pin, that enable pin will be there, so which is used to either enable or disable the logic system, and it may be an active high enable pin or active low enable pin. Usually uh, there will be an active high enable pin, means so whenever a logic 1 input is given to the enable pin, that will enable the logic system, and if you provide a logic 0 to the enable pin, then that is going to disable the entire logic system. So the multiplexers were referred as data selectors, and demultiplexers, these are referred as data distributors, because these are going to distribute a single data over 2 to the power of n possible output lines. So that's why these are referred as data distributors, whereas multiplexers were referred as data selectors, because there were 2 to the power of n input lines were there, and they, out of 2 to the power of n input lines, at any time only one input line was used to be selected based on the content of the selection lines. Here that is exactly in the reverse way. That's why these are referred as data distributors. You can see the logic system here. So here there is only one data input. Data input is there. There is only one data input is there, and there are possible 2 to the power of n possible output lines are there, and there are n control signals. Control signals are nothing but the select lines. You can say select lines are nothing but control signals. There will be n number of select lines, and there is a common enable pin is there, as in case of multiplexers. So here in the diagram you can clearly see there is only one data input is there. So this input has to be routed on any one of the output line among the 2 to the power of n possible output lines. So on which output line this particular data is to be routed on, that depends upon the content of the selection lines. ಸೊ ಅಂದ್ರೆ ಇದರ ಅರ್ಥ ಏನು, ಒಂದೇ ಒಂದು ಇನ್ಪುಟ್ ಇರುತ್ತೆ, ಈ ಒಂದು ಇನ್ಪುಟ್ ಅನ್ನ ನಾವು ರೂಟ್ ಮಾಡಬೇಕು, ರೂಟ್ ಮಾಡಿ ಔಟ್ಪುಟ್ ಲೈನ್ಸ್ಗೆ ಕಳಿಸ್ಬೇಕು. ಈ ಔಟ್ಪುಟ್ ಲೈನ್ಸ್ ಎಷ್ಟು ಇರ್ತಾವಪ್ಪ ಅಂದ್ರೆ 2 ಟು ದ ಪವರ್ ಆಫ್ n ಔಟ್ಪುಟ್ ಲೈನ್ಸ್ ಇರ್ತವೆ. ಯಾವ ಪರ್ಟಿಕ್ಯುಲರ್ ಔಟ್ಪುಟ್ ಲೈನ್ ಮೇಲೆ ನಮ್ಮ ಡೇಟಾ ಹೋಗಬೇಕು, ನಮ್ಮ ಡೇಟಾ ಹೋಗಿ ಕೂತ್ಕೋಬೇಕು ಅನ್ನೋದು ಡಿಸೈಡ್ ಮಾಡೋದು ಈ ಸೆಲೆಕ್ಟ್ ಲೈನ್ ಕಂಟೆಂಟ್ಸ್. ಓಕೆ, and the logic system is written in this form, that is 1 is to 2 to the power of n with n number of select lines. Next we will see the variants, or you can say the types of demultiplexers. So as I told you, this is a 1 is to 2 to the power of n logic system with n possible select lines. So if you provide n as 0, then we will get n as 1, then we will get a logic system 1 is to 2 to 1 is to 2 demultiplexer, and if you put a value n equal to 2, then it will be called as 1 is to 4 demultiplexer with n number of select lines andra 2 select lines. And if you put a value of n equal to 3, then another variant, that is 1 is to 8 demultiplexer will be there with 3 select lines. And if you put n equal to 4, that will be called as 1 is to 16 demultiplexer with 4 select lines. Okay, first we shall see the 1 is to 2 demultiplexer. So as the logic system is represented with 1 is to 2, it means that it will have one input line, one input data line, and 2 output lines, and there is only one selection line which is going to select one of the 2 output lines. Okay, there are the same thing is written here. There are 2 output lines and one select line is needed to select any one of the 2 output lines. So remember, this was input lines in case of multiplexers, but here the same is written for output lines, and there is only one data input line, only one data input line and 2 output lines and one select line. So let designate the outputs with the literals y0 and y1, which are nothing but the output lines, and s with the select line, and d with the only one input, and e with the enable input. Let's see the logic symbol here. You can see here there is only one input, which is designated as D, and there is only one selection line, that is S, which is used to select, whose content is used to select one among these two output lines, and there is an enable pin. Let's see the operation first, then we will discuss the truth table. Let's say since there is only one select line here, with one select line or with only one select line, I can have the two possible values for the select lines, that is it may be 0 or it may be 1. The content of the select line, that is used to decide which output line is to be selected. Okay, let's say if select line content is 0, then y0 is selected and the input information is routed on this line, output line. If select line content is 1, then the input information, that is D content on the data input line D is routed on the output line y1. ಸೊ ಈಗ ಏನಾಯ್ತಪ್ಪ ಅಂದ್ರೆ ಇದರ ಇನ್ಫಾರ್ಮೇಶನ್ 0 ಇತ್ತಪ್ಪ ಅಂದ್ರೆ y0 ಸೆಲೆಕ್ಟ್ ಆಯ್ತು, ಇನ್ಪುಟ್ 0 ಆದ್ರೂ ಇರ್ಬೋದು 1 ಆದ್ರೂ ಇರ್ಬೋದು, ವಾಟ್ ಎವರ್ ದ ಇನ್ಪುಟ್ ಇನ್ಫಾರ್ಮೇಶನ್ ಇಸ್ ದೇರ್ ಆನ್ ದ D pin or D input line is routed on the y0. if select line content is 1 ಇತ್ತಪ್ಪ ಅಂದ್ರೆ y1 ಸೆಲೆಕ್ಟ್ ಆಯ್ತು, ಆ y1 ಮೇಲೆ ಈ ಇನ್ಪುಟ್ ಇನ್ಫಾರ್ಮೇಶನ್ ಹೋಗುತ್ತೆ. So importance of enable pin, as you already know, this is used to either enable or disable the logic system. If it is equal to 1, then this is going to enable this logic system, or if it is 0, then this is going to disable this logic system. If enable pin is made 0, andra if logic system is disabled, then the content of selection lines, there doesn't make any effect on selection on the output lines. So total outputs ಏನಾಗ್ಬಿಡುತ್ತೆ 0 ಇರುತ್ತೆ. So to get the functionality of this logic system, we should compulsorily give an input 1 or active high input has to be provided to the enable pin. So okay, next we shall see the truth table. In truth table ಅಲ್ಲಿ ನೋಡಬಹುದು ನೀವು, if enable pin is made 0, the entire logic system itself will be disabled. Whatever may be the content on D or select line, the outputs they remain 0 ನೇ ಇರ್ತವೆ. Next, in the next two cases, the enable pin is made high. So whenever the enable pin is made high, then the logic system is enabled. Now depends on the content of select lines, one of these output lines is selected and the input information is routed on it. Andre with enable pin equal to 1, D ಏನಾದರೂ ಇರಬಹುದು, it may be 0 or 1. If select line is 0, then y0 is selected and D, the information D will appear on y0. So ಅದಕ್ಕೆ y0 ಏನು ಮಾಡಿದ್ವಿ, D ಅಂತ ಬರೆದಿದ್ವಿ. y1 it is not selected, so its content will be 0. Similarly, in the next combination, again enable pin is high. Whatever may be the D input, it may be 0 or 1, whatever. If the select line content is 1, then y1 is selected. y1 select agi, the data on the data input line D will appear on the y1. ಅಂದ್ರೆ ಇಲ್ಲಿ ನೋಡಬಹುದು D ಅಂತ ಬರುತ್ತೆ. y0 select ಆಗಿಲ್ಲ ಅಂದ್ರೆ ಅದರ ಕಂಟೆಂಟ್ ಏನಿರುತ್ತೆ 0 ಇರುತ್ತೆ. Next we shall write the boolean expressions for the outputs. So since there are two outputs, we are supposed to write two boolean expressions, one for y0 and one for y1. It is very simple. So here we need not to draw any K-map or do any simplification. Simply we should write ಯಾವುದನ್ನ ಬರಿಬೇಕಪ್ಪ ಅಂದ್ರೆ ಯಾವ ಒಂದು ಕಾಂಬಿನೇಷನ್ಗೆ ಅದು 0 ಇಲ್ಲ, ಯಾವ ಒಂದು ಕಾಂಬಿನೇಷನ್ಗೆ 0 ಇಲ್ಲ ಅದಕ್ಕೆ ಕರೆಸ್ಪಾಂಡಿಂಗ್ ಇರುವಂತ ಇನ್ಪುಟ್ ಕಾಂಬಿನೇಷನ್ಸ್ ನ ಜಸ್ಟ್ ಏನ್ ಮಾಡಬೇಕು, ಲಿಟರಲ್ಸ್ ನ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡ್ಬೇಕಷ್ಟೆ. ಇಲ್ಲಿ ನೋಡಬಹುದು y0 it is 0 for the first and third case and it is D for the second combination. So ಈ ಕಾಂಬಿನೇಷನ್ ಗೆ ನಾವು ನೋಡೋದಾದ್ರೆ ಕರೆಸ್ಪಾಂಡಿಂಗ್ ಇನ್ಪುಟ್ಸ್ ಏನೇನು ಲಿಟರಲ್ಸ್ ಇದಾವೆ ನೋಡಬೇಕು. ದಟ್ ಈಸ್ enable E S bar and D. E S bar D. Similarly for Y1, for the first two combination it is 0, so we are not supposed to write anything here. So for the third combination it is D. Simply multiply the literals of the inputs here, that is E S into D. E S bar D, Y1 ಗೆ E S D. So this is the logic diagram. So enable S and D, why not ನೀವು ನೋಡಬಹುದು. So here D will appear here and this is S, and if you invert this it will become S bar. So S bar will come here. Then this is an enable pin which is common to these two AND gates. So this is E S bar D, that is Y0. Similarly for the Y1 it is D will appear here and this is S and this is enable. So that is ESD. So this is about the 1:2 demultiplexers. Next we shall see another variant, that is 1:4 demultiplexer. So as the name itself indicates, this is a system which consists of one data input line and four output lines and two select lines to select one among the four data output lines. The same thing is written here. There are four output lines and two select lines are needed to select any one of the four output lines, and there is only one data input line. So now we shall give the names to the inputs and outputs, are the we will designate them with the literals Y0, Y1, Y2 and Y3. These are the four literals for indicating the output lines. Let S1 and S0 be the select lines and D be the only one data input line and E be the enable input. So this is the logic symbol. You can clearly see here there is only one data input line here. There are four possible output lines. Those are Y0, Y1 and Y2 and Y3. And there are two select lines which are designated with the literals S1 and S0, and there is an enable pin. The logic symbol is clear. Okay. So if you see the operation, so with the two select lines, I can have the four different possible combinations. It may be 0 0, it may be 0 1, it may be 1 0, or it may be 1 1. The contents on these select lines, they are used to select one among the four output lines. So with S1 S0 0 0, Y0 is selected. Then the input information on the D input line will be routed on the Y0. With S1 S0 0 1, Y1 is selected and this input information is routed on it. With 1 0, Y2 is selected, and with 1 1, the last output, that is Y3 is selected and the input information is routed on it. And as we know, the enable pin is always made high. So as it is made high, this logic system is enabled and we can get the functionality out of it. So if enable pin itself is 0, then the entire logic system itself will be disabled. So the information on the D or the information on the select lines, that doesn't make any effect on the output lines, they remain 0. So once we see the operation, it is easy to write the truth table here. So very first combination you can see here, if enable pin itself is 0, the entire logic system is disabled. Whatever will be the content on D, S1 and S0, we don't care the information. So that's why these are indicated with XX, that is don't care. And the output, there it remains 0. All the output lines they remain 0. For the next four combinations, the enable pin is 1, means the logic system is now it is enabled. So once the logic system is enabled, then we should look for the contents on the select lines, that is S1 and S0. For the first combination, the S1 and S0 both are 0 0. So as these two are 0 0, Y0 is selected and the information D, it may be 0 or 1, it appears on the Y0. Similarly with 0 1, Y2 is selected, Y1 is selected, and the input information D, it will appear on the Y1. Similarly with 1 0, Y2 is selected and the information appears on the Y2 line. Similarly with last combination 1 1, Y3, the last output line is selected and the input information, the D input information, it, it is routed on the Y3 output line. So whichever the line that is not selected, its content will be 0. And since there are 4 outputs here, so we will have 4 Boolean expressions for each outputs. So why not? So how to write the Boolean expression for why not? So just simply multiply. So for whichever combination it is not 0, you have to consider, you have to look for such a combination. You know, first and the last 3 combination it is 0. Only for the second combination it is D. So just look for, just multiply these literals E, S1 bar, S0 bar, D. That is the first Boolean expression or the Boolean expression for y naught. Similarly for y1, you can see here only for this combination it is D, it is not 0. Just multiply this combination, that is E, S1 bar, S0, D. That is the second expression. Similarly for y2, only for this combination it is D, for other combination it is 0. So just multiply the combination literals here, that is E, S1, S0 bar into D. Similarly, the last one is E, S1, S0 and D. So now for these Boolean expressions, how to implement this using a logic circuit? So we obviously we need a 4 input AND gate. We will see it here. And since there are literals with the complemented literals are also there, we need a NOT gate as well. So let's see the logic circuit. So this is y0, this is for y1, y2 and y3. Enable pin, it goes as a common input to all the logic AND gates here. You can see this is the first AND gate, this is second AND gate, and this is third AND gate, and this is fourth AND gate. Each AND gate is a 4 input AND gate. So D is you can see here. I will just illustrate for the, I will just ನಾ ಫಸ್ಟ್ ಮಾತ್ರ ನಾ ಹೇಳ್ತೀನಿ, ನೆಕ್ಸ್ಟ್ ನೀವೇ ನೋಡ್ಕೋಬೇಕು. ಇ S1 ಬಾರ್ S0 ಬಾರ್ D ನೋಡ್ಬೋದು. E will go here, so this is the input E, and since this is a not gate here, this is S1 bar and this is S0 bar. S1 bar is another input here, so this is S1 bar. Similarly S0 also is another input here for the first AND gate, so this is S0 bar, and one more on the last input is D here. D is the first input. So if you multiply all these, then I will get the first Boolean expression or the Boolean expression for y0. Similarly, it is implemented for the other outputs as well. Next logic system or next demultiplexer version is 1:8 demultiplexer. In 1:8 demultiplexer, we will have only one input and there are 8 possible outputs which are designated with the alphabets y0 till y7, and there are 3 control lines or select lines. Those are designated as S2, S1 and S0, and there is an enable pin here. With these three select lines, I can have 8 different possible combinations. That is, that will range from 0, 0, 0 to 1, 1, 1. So with select line content 0, 0, 0, Y0 is selected and the D, it appears on the Y0. Similarly, with 0, 0, 1, Y1 is selected. With 0, 1, 0, Y2 is selected. With 0, 1, 1, Y3, so on. If the contents on the select line, that is 1, 1, 1, then the last line Y7 is selected, and the information on the D pin, it will be routed on the last output line, that is Y7. Again, enable pin, it should be connected to 1. So since it's an active high enable pin, it should be always connected to VCCR 1. If you see the truth table, for the first combination, enable itself is 0. So as the enable pin is made 0, the entire logic system is disabled, and whatever will be the content on data input line or the select lines, the output will remain 0. All outputs will remain 0 because none of the output lines are selected and the information on the day input line is routed on it. So that's why all will remain 0. For the next combination, for the next 8 combinations, the enable pin is high. So since the enable pin is high, now the system will look for the content on the selection pins or selection lines. With 0, 0, 0, Y0 is selected. As I told you, the information on the D input line, it will appear on the Y0, and for the rest other output lines, they will remain 0. Similarly, with 0, 0, 1, Y1 is selected. With 0, 1, 0, Y2 is selected. With 0, 1, 1, Y3 is selected. With 1, 0, 0, Y4. Similarly, Y5, Y6. With 1, 1, 1, the last output, that is Y7, is selected, and the information on the D input line, it appears on the last output line Y7. And now we are supposed to write the Boolean expressions for all these 8 outputs. So as I told you, so here we are now ಏನು ಮಾಡಬೇಕಪ್ಪ ಅಂದ್ರೆ, in order to write the Boolean expression for any output line, we should look for the combinations for which combination it is not 0. Only this is the combination for which the y0 is not 0. Just multiply the input literals here, that is enable s2 bar, s1 bar, s0 bar into D. So here I have skipped the enable. You can simply write enable. This enable has to be multiplied with all the Boolean expression. Next we will see the last combination, that is for writing the Boolean expression for y7. Y7 is not 0 only for the last combination, that is enable s2, s1, s0 into D. That is the last combination, enable s2, s1, s0 into D. Now we shall draw the logic circuit for these all 7, so these all 8 outputs. So here we need, what all we need? We need a 5 input AND gate. If you consider enable, we need a 5 input AND gate. So if you, in some books they have omitted the enable pin, enable itself, so there we need a 4 input AND gate. But here if you consider the enable, then we need a 5 input AND gates. So totally such 5 input AND gates, how many number of such 5 input AND gates are required andaga, since there are totally 8 outputs, so we need 8 5 input AND gates to implement these 8 outputs. You can see here. So here the star mark, it indicates those lines are connected with it. You can count the number of inputs for the y0 here, 1, 2, 3, 4 and 5. Totally the 5 literals are multiplied. Similarly for y1, y2, y3, y4 till y7. So here I will just ಯಾವ್ದಾದ್ರು one combination ಹೇಳ್ತೀನಿ. Let's say y7. Okay, y7. So which all lines are connected? Let's see. The first line, this is connected to y7. The first line is nothing but this is enable. So this is enable. Okay. Next, this line is connected. What is this line? What is the content on this line? This is S0. Okay. Let's write S0. Similarly, one more line is connected. This line, it corresponds to a value S1. So this is S1. Similarly, this line, it corresponds to S2, S2. And finally, one more line is connected, that is D. So these all literals have to be multiplied now. That is E into S0 into S1 into S2 into D, which is nothing but the expression for Y. Okay. Next, we shall see the applications of demultiplexers. So demultiplexers can be used as decoder. So, and these are data distributors. So for multiplexers, we told that they were data selectors. Now these are called as data distributors because these are going to distribute the data on one among the 2 to the power of n output lines. So that's why these acts like a data distributor, and it can be used to implement Boolean expression like multiplexers. Multiplexers also were used to implement the Boolean expressions. These are also used to implement the Boolean expressions, and these found their application in the data acquisition system or data acquisition techniques, and these are used in security monitoring system. Again, this question may be asked for 2 marks to 3 marks to write the applications on the demultiplexers. Next, and the important concept is the difference between the multiplexers and demultiplexers. Very first difference, very first two difference, they tell you the number of inputs and the output lines that are required for the multiplexers and demultiplexers. As we know that in multiplexers there were 2 to the power of n data inputs, but in demultiplexer there is only one data input, and in case of multiplexers there is only one data output line, and but here there are 2 to the power of n data output lines are here. So multiplexers were referred as data selectors, and these are referred as data distributors. And the relationship between input and output, this one I have already told you. This is a many to one system, and this can be referred as one to many. And uh, these will convert a parallel data into serial data, means many to one, and this will convert a serial data into parallel, that is one to many. And these are used in time division multiplexing system at the transmitting end, and these are used at the receiving end. Next, we can write few examples for multiplexers. The variants that are available here are 2:1, 4:1, 8:1, or 16:1, and so on. And similarly, the logic systems here, they can be uh, indicated by 1:2 or 1:4 or 1:8 demultiplexer. Again, this is an important question for 5 marks. So this is all about the multiplexers and demultiplexers. Next, we shall see the one more logic combination logic system variant, that is uh, decoder. Decoders are very similar to the demultiplexers. Decoders are the combinational circuits. They have n number of inputs and 2 to the power of n outputs. And here the binary information on the n input lines are decoded into a binary information on 2 to the power of n output lines. So basically it is a n is to 2 to the power of n system, means it will have n number of inputs and 2 to the power of n outputs. So as I told you, these are very similar to the demultiplexer. The only difference is the demultiplexer system is was indicated by 1 is to 2 to the power of n with n number of select lines. But here, instead of only one input, there are n inputs are here, and the number of outputs, if you compare, both are one and the same. Number of inputs are 2 to the power of n only, and here there are n number of select lines are there, and there is no select uh, there are no select lines in case of decoders. So what is the main use of decoder? So basically, the decoders and the encoders, they find their applications in the communication system. So whenever we want to have a data security while sending the information from the transmitter end, we may use decoders. At the receiving end, in order to encode the data properly, the decoded data, we will use encoders. Decoders, they, if they are used in the transmitting end, then the encoders will be used at the receiving end. These are basically used to achieve the data encryption or the data security. Here, the binary information on n input line is decoded into an information on the 2 to the power of n output lines. How it is decoded? So that depends upon the different variants that are available with the decoders. The first decoder is an active high output decoder, and the second decoder is an active low output decoder. In case of active high or logic 1, active high output or logic 1 decoder, so here, according to the information on the input line, binary information on the input line, one among the 2 to the power of n output lines will be active high, and rest all outputs will be 0. ಅಂದ್ರೆ ಇರುವಂತ ಇನ್ಫಾರ್ಮೇಶನ್ ನೋಡ್ಕೊಂಡು 2 to the power of n ಔಟ್ಪುಟ್ ಲೈನ್ಸ್ ನಲ್ಲಿ ಯಾವ ಲೈನ್ ಆಕ್ಟಿವ್ ಇರುತ್ತೋ ಆ ಲೈನ್ ಮಾತ್ರ ಒನ್ ಅಂತ ಇದ್ದು ಮಿಕ್ಕಿದ ಎಲ್ಲಾನು ಔಟ್ಪುಟ್ ಲೈನ್ಸ್ ಏನಿರ್ತವೆ 0 ಅಂತ ಇರುತ್ತೆ. ಅರ್ಥ ಆಯ್ತಾ? ಒನ್ ಔಟ್ಪುಟ್ ಲೈನ್ ಮಾತ್ರ ಇದ್ದು 1 ಅಂತ ಕಂಟೆಂಟ್ ಇದ್ದು ಮಿಕ್ಕಿದ್ದೆಲ್ಲಾನು 0 ಇರ್ತವೆ. And that kind of decoder is an active high output decoder. This is exactly reverse in case of active low output or logic 0 decoder. So here in this kind of decoders, out of 2 to the power of n output lines, only one output line which is active will be 0, and rest all other output lines will be 1. ಅಂದ್ರೆ ಯಾವ ಔಟ್ಪುಟ್ ಲೈನ್ ಆಕ್ಟಿವ್ ಇರುತ್ತೋ ಅದು ಮಾತ್ರ 0 ಇದ್ದು ಮಿಕ್ಕಿದ್ದೆಲ್ಲ ಏನಿರುತ್ತೆ 1 ಅಂತ ಇರುತ್ತೆ. ಸೊ ಯಾವ ಲೈನ್ ಆಕ್ಟಿವ್ ಇರುತ್ತಪ್ಪ ಅನ್ನೋದು ಡಿಸೈಡ್ ಆಗೋದು ಯಾವ್ದ್ರ ಮೇಲೆ? ಇಟ್ ಡಿಪೆಂಡ್ಸ್ ಅಪಾನ್ ದಿ ಬೈನರಿ ಇನ್ಫಾರ್ಮೇಶನ್ ಆನ್ ದಿ n input lines. The same is written here for active high output decoder. Here, for any combination of the binary inputs among the 2 to the power of n output lines, only one output line is at logic 1, and rest all output lines will be at logic 0 state. This is exactly reverse here. Out of 2 to the power of n output lines, only one output line is at logic 0, and rest all output lines will be at logic 1 state. Again, as in case of multiplexers and demultiplexers, here also we will find one more pin, that is enable pin. So this is an active high enable pin, or it may be an active low enable pin. This is used to either activate or deactivate this logic system. So you can see the logic symbol here. It consists of n input lines and 2 to the power of n output lines. Decoder ಅಂದ್ರೆ ಏನಾಗತ್ತಪ್ಪ ಅಂದ್ರ, according to the binary information on the n input lines, out of these 2 to the power of n output lines, only one output line will be active, and rest all output lines will be inactive. Whichever line is active, that will be logic 1 in case of active high output decoder, and it will be logic 0 in case of active low output decoder. So generally, while discussing further, we consider it as an active high decoder, means whichever line that is activated, that will be considered as a 1, and rest all output lines will be active 0 only, or active low only. So as we represented the logic system with n is to 2 to the power of n. So now if you put a value n equal to 1, then we get a decoder 1 is to 2 line decoder, and if you put a value of n equal to 2, then we get another logic decoder system, that is 2 is to 4. Similarly, if n equal to 3, then that is called as 3 to 8 decoder, and if n equal to 4, it is 4 is to 16 decoder. Let us discuss one by one. For first one, that is 1 is to 2 line decoder, it has got only one input and two outputs, and here the binary information on one input line is decoded into a binary information on two output lines. Decoding andre ಏನು, out of 2 to the power of n output lines, only one line will be activated and its value will be 1, and rest all output lines will be 0. We'll see it in the truth table. So let's designate the inputs and outputs with literals. Let a be the input and y0 y1 be the are the outputs, and e be the enable input. Let's see the logic symbol. So here you can see a is the literals, you can give any name. Let a be the input here and e be the enable input. Y0 and y1 are the outputs. Let's see the operation here. So first we shall start the discussion with the enable pin. So if the enable is made high, or if enable is connected to a logic 1 or VCC, the system is enabled, and if it is 0, the entire logic system itself will be disabled. Then the decoding operation will not be done at all. Let us consider E is connected to 1. With a single input, I can have two possibilities. The A can be a value 0 or A can be 1. So it is having only one bit binary information. This binary information is to be decoded onto the output lines, that is y0 and y1. We'll see. So whenever A is equal to 0, y0 is only activated. So since y0 is only activated, y0 will be 1 and y1 will be 0. If A is equal to 1, then the second line y1 is activated, means whichever the line that is activated, it becomes 1, and whichever line that is not activated, it will be 0. Okay, in the truth table you can see here, if enable pin itself is 0, whatever may be the content binary information on the A, it is not decoded on the output lines y0 and y1, and they remain 0. None of the output lines are activated whenever enable pin itself is 0. So next, for the next two combinations, you can see here, if enable pin is 1, then if the binary information on the input line is 0, then y0 is activated, means it is made 1, and y1 is not activated, so that's why it will be 0. And if A is 1, then y1 is activated, so that's why it is 1, and y0 is not at all activated, so that's why it is 0. And now if you want to write the Boolean expressions for the outputs, since there are two outputs, we expect two Boolean expressions. While writing the Boolean expressions, again like in demultiplexers, we may not need to write a K-map and do the simplifications. Simply, for which all combinations it is not 0, we just have to multiply the literals, input literals here. You can see here, it is 1 for, y0 is 1 for only for this combination, that is E into A bar. E multiplied with A bar. Next, y1 is not 0 only for this combination, that is 1 1, that is E into A. And if you write the logic circuit here, you can see here, Why we need a two input AND gate, two input AND gates. This is first AND gate and this is second AND gate. You can see the connection here. So this is A bar. The star mark, it indicates the connection. A bar is connected here and A bar it appears here, and E is again one more input for the first AND gate. So Y0 will become E into A bar. Similarly for Y1 you can see here there is a connection made for the A input line here as well as E here. This is nothing but the product of A into E, which is nothing but Y1. So this is about 1:2 decoder. Next, 2:4 line decoder. So it consists of 2 inputs and 4 outputs, and the binary information on the 2 input lines is decoded into a binary information on 4 output lines. You can see the logic symbol here. So here A and B are inputs, D0, D1, D2 and D3 are the outputs, and E is the enable pin here. If you see the operation, whenever enable is equal to 0, irrespective of the content on A and B, the none of the output lines will be activated, means all will remain 0. If enable pin is high, then according to the binary information on the input lines A and B, only one among the 2 to the power of n output lines will be activated and it is made 1. The rest other output lines which are not activated will remain 0. If A and B both are 0 0, then D0 only is activated and it is only made 1, while D1, D2, D3 will remain 0. So that you can see here, if A and B both are 0 0, only D0 is activated. So this is 1 and rest all outputs will be 0. Similarly for 0 1, if A and B are 0 1, then D1 is selected or D1 is activated. So D1 only will be active high, rest all output lines will be active low only. Similarly for the last combination with 1 1, with 1 1, D3 is activated and it is only 1 and rest all outputs will remain 0 only. And again, as in the previous case, if you write the Boolean expressions for D0, it will come out as E into A bar into B bar. That is the first one. For D1, it is E into A bar into B. That is second one. And for the D2, it is E into A into B bar. And the last one, that is E into A into B for D3. And if you write the logic circuit, it looks like this. So please analyze yourself. Next is the 3:8 line decoder. It consists of 3 inputs and 8 outputs. The binary information on the 3 input lines is decoded into a binary information on the 8 output lines. So let A, B, C be the 3 inputs and D0 to D7 be the 8 outputs and E be the enable pin. So here also, whenever enable pin is made 0, irrespective of the content on the binary information on the A, B and C, all output lines will be active low only. If enable pin is made high, then according to the binary information on the input lines A, B and C, only one among the 8 output lines will be activated and that will be active high. Rest all output lines will remain 0. You can see here for 0 0 0, D0 is activated, that's why it is only 1, that is made 1 and rest all output lines are 0. So if you go on writing all the combination for the last combination with 1 1 1 1, with ABC 1 1 1, the last output line D7 is activated and that is only that only becomes 1. Rest all outputs lines will remain 0. Again, as in the previous case, here we are supposed to write 8 Boolean expressions. Since there are 8 outputs are here. So you are supposed to write the Boolean expression for a combination for which it is not 0. So this is the only combination for which the D naught is not 0. So now we have to multiply the input literals, that is E into A bar into B bar into C bar. You can see here D naught is E into A bar, B bar, C bar. For the last combination, that is for the, if you want to write the Boolean expression for the D7, so this is 1 only for the last combination, and if you multiply the input literals here, that is E into A into B into C, that is for D7. And here we require a 4 input AND gate to implement its logic circuit. So this is the logic circuit. So please analyze this logic circuit yourself. Thank you.